So perhaps the most important derivative in all of calculus is the derivative of e to the x being equal to e to the x. It's the only function where its derivative is itself. This also means if you keep on taking derivatives repeatedly, it's still the same function, so the second derivative of e to the x is still e to the x. And this applies to the third derivative and the fourth derivative, and so on. This is actually a pretty remarkable property, and it's also one of the first things introduced when learning basic derivatives. What I want to do today is actually prove that the derivative of e to the x is indeed e to the x. So first of all, let's actually define what Euler's number e is. The foundational definition of e is the limit as n approaches infinity of 1 plus 1 over n all raised to the power of n, and this converges to approximately 2.718. The fact that this limit converges to a single value is a proof in itself, but I'm just going to assume the foundational definition of e for this video. If we substitute m equals 1 over n, we can come up with an alternate definition of e. In the original limit, we have n approaches infinity, and that's the same as 1 over n approaches 0, which is equivalent to m approaches 0, since m equals 1 over n. If we substitute m equals 1 over n into the expression 1 plus 1 over n to the n, the entire limit becomes the limit as m approaches 0 of 1 plus m to the 1 over m. Since 1 over n is replaced by m, and if m equals 1 over n, then n equals 1 over m. So the exponent of n is replaced by 1 over m. So the entire limit becomes the limit as m approaches 0 of 1 plus m to the 1 over m. This is the same limit as the original one and still converges to e. So we're going to be using this alternate definition of e later in the proof. So to start the proof, we should first apply the limit definition of the derivative to find the derivative of e to the x. So recall that the limit definition of the derivative for any function f of x is d by dx of f of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we apply this to the function e to the x, we get that the derivative of e to the x is the limit as h approaches 0 of e to the x plus h minus e to the x all over h. If we use a property of exponents, we can rewrite the e to the x plus h term as e to the x times e to the h. We can also factor an e to the x term from each term in the numerator, so this just becomes the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. The limit is in terms of h, so the e to the x term, which is in terms of x, can be treated as a constant, so we can bring that to the front of the limit as a constant multiple, so this becomes e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Alright, so all we really need to do now is to find the limit as h approaches 0 of e to the h minus 1 over h, since e to the x can be treated as a constant, and it's not part of the limit anymore. So if we plug in h equals 0, e to the h becomes e to the 0, which equals 1, and 1 minus 1 equals 0, so the numerator would equal 0. And if we plug in h equals 0, the denominator just becomes 0. So we would have a 0 over 0 indeterminate form, which means we could normally use L'Hopital's rule, but in order to do that, we would need to know the derivative of e to the h. And that's the derivative we're trying to prove, so we can't use that, because that would be circular logic. So we need to find a way to find this limit without using L'Hopital's rule. So to deal with this limit, let's substitute m equals e to the h minus 1. If we add both sides of this relation by 1, we get e to the h equals m plus 1, and if we take the natural logarithm on both sides, we get h equals ln of m plus 1. In the limit, h is approaching 0, and as h approaches 0, e to the h minus 1 just approaches 0. Since if we plug in 0 to e to the h, that's just e to the 0, which equals 1, and 1 minus 1 equals 0. So e to the h minus 1 approaches 0. And since m equals e to the h minus 1, this just means m approaches 0. If we plug all of this back into the limit, we get the equivalent limit of the limit as m approaches 0 of m over ln of m plus 1. So the e to the h minus 1 is replaced by m, and since h equals ln of m plus 1, the denominator becomes ln of m plus 1. If we multiply both the numerator and denominator by 1 over m, the limit becomes the limit as m approaches 0 of 1 over m times ln of m plus 1. Using the power rule of logarithms, we can rewrite the denominator as ln of m plus 1 to the 1 over m. We can use limit laws to bring the limit into the logarithm to rewrite this as 1 over ln of the limit as m approaches 0 of m plus 1 to the 1 over m. I'll show why we can do this later, but I'm going to assume we can do this for now, and it'll be easier to show that we can do this when we have found the limit already. So earlier, we established the alternate definition of e as the limit as m approaches 0 of 1 plus m to the 1 over m. If we use that, the value of the limit as m approaches 0 of m plus 1 to the 1 over m in the expression becomes e, so the expression becomes 1 over ln of e. Ln of e is equal to 1, so the entire expression is just equal to 1. So the limit as h approaches 0 of e to the h minus 1 over h equals 1. So earlier we had the step, the limit as m approaches 0 of 1 over ln of m plus 1 to the 1 over m equals 1 over ln of the limit as m approaches 0 of m plus 1 to the 1 over m. So now I'm going to prove to you really quickly why this is actually the case. So earlier we established that the limit as m approaches 0 of m plus 1 to the 1 over m equals e. So this limit definitely exists, and ln of m is continuous at e. So we can use the property for dealing with function composition when dealing with limits. So the property is, if the limit as x approaches a of g of x equals b, and the function f is continuous at b, then the limit as x approaches a of f of g of x equals f of the limit as x approaches a of g of x, which is equal to f of b. So since the limit as m approaches 0 of m plus 1 to the 1 over m exists and equals e, and ln of m is continuous at e, the limit as m approaches 0 of ln of m plus 1 to the 1 over m, which corresponds to the limit as x approaches a of f of g of x expression, equals ln of the limit as m approaches 0 of m plus 1 to the 1 over m, which corresponds to the f of the limit as x approaches a of g of x expression. So this is just equal to ln of e, since we know that the limit as m approaches 0 of m plus 1 to the 1 over m equals e, and this is just equal to 1. So the limit as m approaches 0 of ln of m plus 1 to the 1 over m definitely exists. So the limit as m approaches 0 of 1 equals 1. So the limit definitely exists, since it's just a constant. And we can conclude that the limit as m approaches 0 of 1 over ln of m plus 1 to the 1 over m equals the limit as m approaches 0 of 1 divided by the limit as m approaches 0 of ln of m plus 1 to the 1 over m, since both the limit in the numerator and the limit in the denominator exist, which we showed earlier. And this is just equal to 1 over ln of the limit as m approaches 0 of m plus 1 to the 1 over m, since in the numerator, the limit as m approaches 0 of 1 just equals 1. And we just showed earlier that the limit as m approaches 0 of ln of m plus 1 to the 1 over m equals ln of the limit as m approaches 0 of m plus 1 to the 1 over m. So after doing all of this, we can conclude that the limit as m approaches 0 of 1 over ln of m plus 1 to the 1 over m is indeed equal to 1 over ln of the limit as m approaches 0 of m plus 1 to the 1 over m. We needed to ensure that both the limit in the numerator and the denominator exists, because the limit law, which we used, only applies when both limits exist. So this proof was definitely long-winded, and it seemed like we needed to do the proof backwards, but I don't like to leave anything out. So previously, we started off with the limit definition of the derivative of e to the x, and after some algebra, we found that the derivative of e to the x is e to the x times the limit as h approaches 0 of e to the h minus 1 over h. We also found that the limit as h approaches 0 of e to the h minus 1 over h equals 1. So this expression is just equal to e to the x times 1, which equals e to the x. So we started with the derivative of e to the x, and after doing a number of steps, we ended up with e to the x. So the derivative of e to the x is indeed e to the x.